So when you think about mainframes, so the words that would typically come to your mind are probably old, expensive, outdated, complicated, and you probably wouldn't be thinking about them in a cloud-native context. And hopefully today I can convince you that mainframes are indeed still relevant and they have their place in the cloud-native world. And before we get into it, I need to give a quick shout out to the whole project team. So especially one of my colleagues here, Yannick, who is all the way on the right, and he was working with me on this Kubernetes on mainframe part of the project, especially in the beginning. And he's really good at rubber ducking and asking the right questions. And speaking of questions, these are the questions I want to answer today. So. First, I'd like to get a common understanding a little bit about what mainframes really are. We'll answer if they still matter, how they work, why you would want to put containers on them in the first place, and then finally, how do you actually put containers on them? So you're probably asking yourself, aren't mainframes just legacy infrastructure nowadays? And yes, but also no. Yes, they're legacy because they've been around since the 50s. They still run COBOL. They're often tied to old school institutions like banking, government stuff, insurance. And a lot of their workloads that were written decades ago are still running, and they're completely untouched as they are. They're not trendy at all. They don't fit the modern break fast, move fast and break things type of mentality. But also no, because they're still evolving and modern mainframes can run Linux. They support cloud integration. They have AI acceleration, which I hear is trendy right now. And they can process absurd amounts of data with better efficiency and reliability than huge racks of x86 servers. And the companies that need that kind of crazy reliability, security, and just raw transaction power still buy new mainframes to this day. And they're not going away for now. They're just invisible because they just work and they're not as hyped as some other technologies. But aren't they just big, expensive servers? Well, kind of. Not exactly. They're kind of like the computing equivalent of a nuclear bunker because they're ultra reliable and disaster proof. So IBM tests their components against earthquakes and radiation, so they can technically withstand solar flares. So the joke we always have is like that the mainframes will outlast us in a catastrophe. So and the high-end mainframes also have things like battery backups and self-contained redundant water cooling systems. And actually, IBM mainframes were the first enterprise appliances back in the day to introduce water cooling. So the running gag used to be that if you have a problem with your mainframe, you call a plumber and not an engineer. And their hardware and firmware and OS are really finely tuned to each other and built for these sort of mission-critical workloads and the kinds of workloads that are impractical to handle in a distributed way. So the most common use case is really credit card transactions and ATM withdrawals where you don't want to leave people waiting for too long. And in fact, 90% of all credit card transactions are still handled by mainframes, and 71% of Fortune 500 companies still use them, and almost 70% of all production workloads still run on mainframe. Okay, so I hope we've established sort of basic common understanding that what mainframes are and can agree that they at least still matter somewhat for some people. But how do they actually work and what makes them special? So on a hardware level, all the components are very fine-tuned, as I already said. And they can do really crazy things, like you can hot swap CPUs while the thing is running, which I think is really impressive. And the SLA that they build these mainframes for is 7 nines, which is about 3 seconds of downtime per year, which is pretty impressive to me. And they also have cool things like these onboard crypto modules. So you can, it's kind of like a built-in HSM, so you can handle things like encryption and related tasks on the same machine. Yeah, you could talk about this for really long, so I'll cut it short for the sake of the presentation. And then on the systems level, the key takeaway is really that you can run all sorts of different workloads on them, either natively or virtualized. And depending on the hypervisor technology, with almost no overhead. So in this diagram here, we can see some KVM workloads, some ZVM stuff, and also native Linux on LPAR. So an LPAR is a logical partition of compute on the mainframe, and it kind of behaves like a VM, but it's a layer below the hypervisor layer, so closer to the bare metal. So there's a type 1 hypervisor that is baked into the firmware, and the LPAR gets direct access to a slice of CPU, memory, and I/O resources. Okay, we have a basic understanding of how they work, and now let's make the jump to containers. This is KCD after all. Why would you want to run containers on a mainframe in the first place? So one reason would be modernizing legacy apps, so running microservices alongside old school COBOL without breaking stuff, breaking dependencies. Security and isolation, so the built-in encryption is better for sovereign applications than like cloud infrastructure that is multi-tenant. Low latency, so running containers next to these old mainframe databases means faster transactions. And it's also a cloud alternative, so you have cloud-like agility with Kubernetes on a mainframe without leaving your own data center. And depending on the workload also, you can have cost savings. So the specific use case I was working on was for a hyperscaler that was using these mainframes for confidential containers on top of OpenShift sandbox containers, which is the downstream project of Kata that you might be familiar with. And Kata containers are basically just containers that run inside of a confidential VM using the hardware-backed trusted execution environments. And why is this necessary? Normal containers aren't really super isolated. So you share the kernel and trust the host, and Kata kind of fixes this gap by running these containers inside a VM with confidential computing stuff that the host can't peek into. And Kata is made out of three core components. So the CPU level features that are used to encrypt memory and block host access, the attestation service that verifies the workload owner and that the container is running in a trusted environment before starting, and then finally the encrypted image pools and file system. So images and secrets can be encrypted and decrypted inside of this trusted execution environment only. And yeah, for my use case, we were using IBM HyperProtect. It was like a secure enclave that is part of the mainframe for the attestation service. Like in a typical deployment, you usually rely on a different cloud provider to handle the attestation service, to have that kind of separation of concerns. All right, so how do you actually put containers on a mainframe? So there are different ways of achieving this. You can do it natively using ZOS container extensions, which I learned about during this project. It's actually Docker Swarm under the hood, which I find really fascinating. And but we're at KCD, of course, so I'll of course tell you about two ways that I use to put Kubernetes on the mainframe. One quick detour. So a big differentiator on the software side of things and a bit of an initial hurdle in this is the system architecture. Similarly to how a lot of things didn't and to some extent still don't work on Apple Silicon. There's a difference between x86 architecture and the S390X architecture that the mainframe uses. And the first draft of this slide was just a comparison table to explain the different features, but I found that a little bit too dry, so I thought I'd explain the differences with a little bit of an animal analogy. So S390 is kind of like an octopus because it has this insane parallelism that it enables. So all the tentacles act independently but coordinated. So it's a crazy multitasker. It's efficient at context switching like an octopus. And you have slick hardware-assisted sleight of hand, like an octopus that can blend into its environment, and fault tolerance. So if an octopus loses a tentacle, it can just grow it back. And x86 in this comparison is kind of like a raccoon, a domesticated raccoon. So it does a lot of things, but it's not always the cleanest. It's a little less efficient. It can do 10 things, but will end up breaking something. And IOPS maybe panics under load. And in terms of fault tolerance, if you cut off a finger, then it's not growing back. You have to take it to the vet or reboot. Right, so the first way I tried was using a regular x86 cluster and then joining a ZVM worker to it. It's easy, right? After all, it's just another Linux machine. You install some packages, enable some systemd units, and it will join the cluster. Actually, yes, it was surprisingly easy. So yeah, you can literally just do that. And, this example was some vanilla Kubernetes on Ubuntu bare metal hosts and a Ubuntu ZVM. And the only real obstacles were deploying the CNI to be multi-arch and adding some labels to the nodes. And it worked fine. And yeah, here we can also see an S390 workload running on the cluster. And the second way was almost the same scenario, but using an LPAR worker and an OpenShift cluster. It's also easy, right? No, unfortunately not. So there are some fundamental differences, and they're kind of related to each other. So OpenShift uses CoreOS, which is Red Hat Enterprise Linux, but super optimized to run Kubernetes and comply with all these like enterprise requirements. And the second reason is that LPARs hate me. And by hate, I mean they're very particular about how they will boot an operating system and how not. And I'll explain this a little bit. So if we try booting an LPAR with just a regular off-the-rack ISO, nothing will happen. So to boot it, we need two files. We need an instruction file which specifies the kernel, the init RAM disk, and a parameters file along with some memory load addresses. And the parameters file contains really just kernel boot parameters that are required to actually start the system. And here in this example, it's on multiple lines, but as I was working on the project, I learned it has to be just one line because I was getting confused why I was only evaluating the first line of parameters every time. So yeah, it has to be one line. And the real thing is also a lot longer because CoreOS wants a lot of parameters to work correctly with mainframe hardware. And yeah. Also, this slide, there's a bug in this slide, and there's a prize if you can spot what the bug is. I'll give you a moment to take a look.
You don't have the DNSIP defined?
No, it's simpler than that even. Okay. Actually, the paths are wrong. So the image files are in the Pixie boot directory, but in the instructions file, it's referencing files that are not there. And apparently it's been this way since 2020, and no one has noticed because no one has ever tried doing this before, except me. So yeah, the correct file ended up looking like that, so I was able to just correct it. And being a Red Hatter, of course, I went to bother the engineers on Slack about this, and they actually fixed it the same day, which was really nice. Okay, so once we have a working ISO that is actually bootable, how do we get the ISO into the mainframe? So I actually had networking issues. The recommended way to do it would be using SFTP or something, so you can actually iterate quickly. But yeah, because the networking wasn't working, I had to build an ISO every time I made a change and then upload it to the HMC over network, over like VPNs, which took about an hour or something each time. And if you leave the HMC unattended for too long, then it will log you out and you have to do it again. And it's really painful. So SFTP is really recommended. And eventually we got the network to play nice, and I was able to boot through SFTP, and was a huge time saver, a huge improvement. Okay, and then the setup for the actual boot kind of looks like that. So the storage system is like a fiber channel storage system that is the install target. That's where we actually want to install the operating system to. And to boot, we need an ignition file that is configuration that is read from a source of truth, like a remote URL, and it applies some configuration, like partitions some drives and sets up users, sets up some systemd services, etc. And we had some issues there as well over the networking because the cluster is using self-signed certificates, and so either you disable a security feature, which we ended up not doing, or you host your own ignition files, not on the cluster endpoint, but on a web server. That's what we ended up doing. And it also made sense in the end because I had to tune the ignition a little bit to trust the custom CA, and I had to write a systemd service for that and bake it into the ignition to make that work. You can also do fun things like add an SSH key to the node at that point, which is really handy when you have to troubleshoot more later on. Yeah. So yeah, those are the components. We load the boot files from SFTP. The install works on the LPAR, talks to the cluster to get the config, and then writes it to the storage system. Yeah, these diagrams are usually a little bit dry. This is what it looks like in real life. So on the left side, we can see the back of the mainframe. You can see all these like big tubes of the cooling system. It looks really impressive. And then on the right side, or no, in the middle, is the storage system that is connected to the mainframe. And not pictured, because I didn't think of this in the time when I was in the data center, is the x86 cluster. And also the jump host that has the web server and SFTP on it. And now, once we have that running, we can observe the install process in this beautiful console. And after the initial install, just change the boot device from the ISO to the SAN device we just installed to, and reboot. And with those hurdles overcome, we now finally get a certificate signing request that we just need to approve for the node to join. And we've come quite far. There are still things that can go wrong, like if some daemon sets are not starting, but those are all problems that can be solved with just like setting the kernel parameters the right way. So I'll spare you those details. And equipped with that knowledge and experience, the process is not quite as hard anymore, but things are always harder when you have to do it for the first time. But yeah, we were successful. We added a a worker LPAR to the existing cluster. Yay, it works. So to wrap the things up we covered today, we talked about what mainframes are. We've established that they still matter to some extent. Talked a little bit about how they work, why you would put containers on them, and then explored how to actually put containers on them along with some of the hurdles that come with that. So what's next? Hopefully this talk got some of you interested in learning a little bit more. So I have a couple links for you for good resources if you want to learn more about modern mainframes and confidential containers. There's the Open Mainframe project, which is an initiative by the Linux Foundation, which is really cool. You can actually get your own ZVM, so like a mainframe architecture VM to play around with for free for 6 months, I think, through them. If you have like an open source project you want to run on mainframe or just mess around with a mainframe for once. There's Project Ambitus, which is also part of that focuses on porting open source software to mainframe. The Linux One Community Cloud is what I was just talking about, where you can play around with ZVM. And then finally, OpenShift Sandbox containers. I have a good Red Hat documentation page for you as well if you want to read more about that. And yeah, we have time for questions now. If you want to see the slides, you can find them on my website or get in touch.
Okay, thank you very much. We have a few questions on Slido already.
That is an excellent question. That is something we should really do.